Okay, let's start, and we prove the main result of this project, this theorem 2 of linear independence of radicals. Yeah. So we have already discussed that theorem 1 is equivalent to theorem 2. Yeah, and maybe we just show theorem 1 above about it more general situation. Yeah, Sergey, can you scroll up? No, above. Yeah, we just show theorem 1 and theorem 2 at the same time. Yeah, simultaneously. Yes, actually these theorems are equivalent to each other, and it's easy to prove it. It seems that theorem 1 is more general, but actually it's equivalent, and most of participants successfully proved it. So we start with theorem 2. Okay, and its proof is splitting into several steps, similarly to the square case of square radicals. So scroll down, please, to section 3, third section, the general case. Yeah, yes, this one. Okay, thank you. The first step is splitting of the last radical. We reduce theorem 2 to the linear independence of powers of last radical. So we will prove theorem 2 prime. You see, yeah, bold theorem 2 prime. In the notation of theorem 2, the numbers 1, Rn, etc., Rn in k minus 1 power are linear independent over field Q of R1, Rn minus 1. It's easy to show that this equivalent. Actually, we need to prove that theorem 2 is following theorem 2 prime implies theorem 2. Yeah, and you see it's quite technical proof. We rewrite an arbitrary linear combination of our radicals, of our products of radicals, more precisely, as polynomial of one of the radicals, last radicals, yes, and use a simple induction. Okay, how to prove theorem 2 prime? The next step, yeah, is to show the following. Let's figure out when powers of some radical are linearly independent over some field k. So now k is arbitrary field, r is arbitrary radical, so, some number such that r in k is in k, big K. Yeah. So what does it mean? That numbers 1, r, etc., r, and k minus 1 are linearly independent over k. It means that r must not be a root of a polynomial with degree less than k and coefficients from big K. If k equals 2, that it means merely that r doesn't belong to k. Yeah? But the general case, when k is more than 2, the situation is this case is much more complicable. So we in this moment we come to algebraic numbers and polynomials. Yeah? I don't repeat standard definitions and properties of minimal polynomials, at least with proofs. Yeah, just remind basic properties we use in the proof. First, minimal polynomial is irreducible. every polynomial over k with root alpha is a multiple of minimal polynomial of alpha, and it gives us that irreducible polynomial over k with root alpha is actually is a minimal polynomial of alpha. Just simple corollary. So we reduce our problem, our condition 7. Maybe scroll up, please, for a while. Yes, this scroll down, please. 7, condition 7. And now our purpose is say, scroll up, condition same. So condition 7. Yes, this one. Stop. Okay. Condition 7. Yeah, we need to rewrite this condition in terms of polynomial. Yes, and now we scroll down. More. Stop. Yes. A little bit. Yes. This condition 7 is stop. Yes, is equivalent to the fact that a minimal polynomial of R is a binomial x and k minus r and k. That is, this binomial is irreducible over k. So let us figure out this irreducibility. In order to understand when this binomial is irreducible over k, we use complex numbers. Though all our heroes are real, both field k and radical r, they're in real numbers, but we need to use complex numbers. More precisely, we use Moore formula. We decompose this binomial in linear factors. So, and using that, we can prove the following lemma, lemma 2, or problem 4.6 in the project. Let k be a subfield in R. R is a radical, and k such minimal number such that R and k belongs to k, big K. So in this case, binomial, our binomial is irreducible over k. Indeed, if we suppose that there is some factor of this polynomial over k, yes, with some degree L less than k, then we consider its free term. Let's call C. And this as we see in this decomposition 8, yes, C equals to some power of minus R and some power of primitive root from unity, epsilon. But k and r both are real, so we get that C and C is real as well. Of course, C belongs to k, of course. So it means that power of R in L belongs to k, but it contradicts to the condition of the lemma. So we prove this lemma. Okay. Yes, and we note that if R doesn't belong to R, if R isn't real number, yes, then lemma fails. Yes, you see counterexample with binomial x cubed minus 1. Okay. So this lemma allows us to reduce theorem 2 prime to the theorem 2 with 2 primes. The following formulation: powers of radical Rn from the first one to k minus 1, all these powers don't belong to this field, which is obtained from Q within joining previous radicals. We prove it by induction on n. If n equals to 1, it's just lemma 1. So what if n more than 1? The next important step is to remove all the irrationality from the denominator. We need to write all numbers of this field as polynomials. I've already discuss this example and this lemma, so we can scroll down. Now I formulate this theorem. Yes, you see, and maybe we formulate this in geometrical terms. If number alpha is algebraic over field K of degree K, then every number from the field K of alpha is uniquely expressed as follows, as polynomial over K. It means that powers of alpha, 1, alpha, alpha square, etc., form basis of this extension, K of alpha over K. The proof is application of Euclidean algorithm. Okay, now using this lemma, we can formulate theorem 2 primes, in the following way. Stop, please. Okay. We removing irrationalities from the denominators. Consequently, we write every number from this field in the as a sum of numbers of the following form. Some linear combinations, some linear combination of products of radicals with rational coefficients. So suppose that condition 9 fails. That is power Rn in L for some L equals to this sum. We note that this sum contains more than one summand. Otherwise, we get contradiction immediately with lemma 1. So, one of radicals, R1 or etc. R minus n minus 1, appears in two summands with different degrees. Let it be Rn minus 1. So we rewrite 9 as following: 12. Rn in L equals to some polynomial of Rn minus 1 with coefficients a0, a1, etc. And at least two of them are non-zero. This is main part of the proof. If k equals 2, then we just square this equality, yes, and we get contradiction very easily. But what to do if k more than 2? We need some concepts, some theory. I will already discuss this example, yes, example 7. Yes, how to get contradiction from this equality. We consider minimal polynomials and get that a equals to 0, and this contradiction. In general case, we need to find conjugates to the right hand side of 12. Please scroll up again. 12. Yes, it's not obviously immediately even that right hand side is algebraic numbers over k. But how to prove it? In order to prove it, we first find conjugates to this number, and this is last basic lemma. I don't remember number of this theorem in the project. Maybe maybe 2.13. Yes, and okay, scroll down. So we defined conjugates of every algebraic number alpha over k. This is just all the roots of the minimal polynomial of alpha, and we denote by sigma of alpha some of them. So it's easy to show that they are different numbers using derivation, but actually this is not used in the proof. Okay, this is example 8. You see, this is just example of how to divide roots into classes of conjugates over different fields. One of the problem in the project. Yes, okay, and now let's formulate a main lemma, and maybe before we consider one more example. 11, I think. Yes, this is example. Yes, example 11. Yes, this is partial case of our situation. Let's disprove this equality. How to do this, and how to find conjugates to the right-hand side. It looks like Cardano formula for cubic equation. Yes. So you see this polynomial f of x, and you see how we find conjugates. In order to prove it, we consider one more polynomial, which is obtained from f by replacing number cubic root of 2 with intermediate y. This polynomial, resulting polynomial, doesn't change under substitution of y epsilon instead of y. Yes, hence y appears in it only with degrees divided by 3. So we replacing y cube by 2 backwards, we get a polynomial over q. So f of x is a multiple of minimal polynomial of cubic root of 3, that is x cubed minus 3, and degrees of these polynomials are the same. So f of x is actually x cubed minus 3. And then we compare the sums of these polynomials, and we have that a equals to 0, because sum of roots of right hand side equals to 3a, and coefficients at x square of x cubed minus 3 is equal to 0. So a equals to 0, and we get such equality. The second, yes, this one, and we divided it by cubic root of 2 and get this equality, and we can get contradiction in similar way as we did in, for example, 7. We obtained that b equals to 0, and now it's this equality is impossible by lemma 1. So this example hint to find how to find conjugates to every algebraic numbers, to every polynomial of given algebraic numbers. This is lemma 5. If we have a list of conjugates for given alpha over some k, over some field k, and f is a polynomial over k, then f of alpha is algebraic over k, and list of its conjugates is the following: f of alpha 1, f of alpha k. More precisely, each of these numbers repeats the same time. So we will prove this equality 14. how to prove it? Actually, we need to prove this. Actually, to prove partial case of this equality when alpha is root, is a radical root of binomial. The proof in this case is easier a little bit, and similar to example considered above. So we consider this polynomial g of x and y, and we note that it doesn't change under replacement of y by y epsilon, because factors are moved cyclically. Hence, all degrees of y in this polynomial are multiples of k. So this polynomial is a polynomial with coefficients in k and the root f of r. So we prove that f of r is algebraic over k, and moreover, its minimal polynomial divides g. So as a corollary, we have that all conjugates with f of r belongs to the set f of r, epsilon, etc. There are no other conjugates, but we need to prove that all these numbers are conjugates indeed. In order to do this, we consider the following polynomial in the point 2, composition of minimal polynomials for f of r and f of x. This polynomial has coefficients over k, obviously, and the root r. So it's multiple of minimal polynomial of r, that is binomial xk minus rk in this case. So all roots of this polynomial are roots of this composition. So we finish the proof of this point. What do we know? What do we need to prove is we need to figure out with repetitions. Yes, last one, third point. How to prove it? We suppose that d is a least integer with the following condition. This is a minimal number such that d's power of minimal polynomial of f of r divides a polynomial g of xr. And we prove that actually these polynomials are equal to each other. Indeed, in the opposite case, the fraction, such fraction is a polynomial over k, and having a root f of r epsilon j for some j, and therefore this fraction is divided by minimal polynomial of f of r. Yes, and this contradiction with minimality of d. So we finish the proof of this lemma in partial case of binomial. The proof in general case, the proof is the same, almost the same, but we need to consider a little bit another polynomial g, you see on the screen, and use the theorem of symmetric polynomials. Okay, now we continue. Consider this equality and equate. We consider 15. Please, yes, scroll up. Yes, this one, and we equate sums of roots of left hand side and right hand side. So scroll down. Yes, here comparison of sums of roots. Recall a sigma of some number is a sum of all conjugates of this number. So you see that d sigma of f of r is a sum of roots of left hand side, and now we calculate the sum of conjugates for right hand side when f of x has the following form. Yeah. So you see, we calculate, we see that sum of these numbers equals to C0 multiple by k. Yes, number of them is k, and other summands equals to 0. It's trivial, and so we have the following equality: 16. The sum of conjugates with every number of the following form: C0, C0 plus C1 R, etc., equals to, no, is proportional to C0. Actually, it's sufficient with some rational positive number. And now we can finally arrive to contradiction in 12. First, we divide 12 by power of radicals, power of radical r n minus 1, such that yes, aj is a first non-zero coefficient, and we divide by g power. And recall that there are at least two non-zero coefficients. Yes, it's very important. So we denote k this field, obtaining from q by adjoining n minus 2 previous radicals. R is left hand side, and we note that R doesn't belong to k, because otherwise, in view of linear independence of radicals r n minus 1 and its powers, we get that r equals to aj and other coefficients a equals to 0. And it's impossible, because we have at least two non-zero coefficients. So r doesn't belong to k, but r in k belongs to q, and in particular to k. So it means that sum of conjugates of this r of this number equals to 0, because there is a polynomial, there is a minimal number m such that r in m belongs to k, and in this case binomial x in m minus r in m is reducible over k, and so this is minimal polynomial of r, and so sigma of r, sum of conjugates, equals to 0. Nice. But sum of conjugates for right hand side is proportional to aj, as we showed. So this is contradiction. And we finish proof our main result. Okay, thank you. Any questions? Or we need to finish? Yes, already. If somebody has some individual questions, maybe we can discuss later.
Yes, because we have one minute for questions.
Yes.
After that starts next.
Yeah, if you have some question about your papers, your solutions, you can ask me, for example, write me on email. Yeah. Thank you for your attention.
All the best to all of you.
Yes, thank you. Goodbye.
Bye.